I'm Ian Ross. I'm a data engineer here in the Center for High Throughput Computing. Those of you with long attendance histories and equally long memories may remember me standing up here 7 and or 8 and or 9 years ago talking about Geo Deep Dive, which is a text data mining platform. Still around. We've rebranded to XDD. I'm the technical lead of that, but today I'm going to be talking about applications of our tried and true and favorite high throughput computing principles to machine learning. So where are we going to go today? I'm going to give a comically brief overview of artificial intelligence and machine learning. I'm not going to stand up here and talk through transformer architectures or tell you why GPUs are so important, but I think it is important to do a little bit of level setting, especially given the recent explosion in LLMs and interest in this space. Then I'm going to talk about what exactly throughput computing or throughput machine learning is, specifically targeting 3 different sort of some true, some stretched hypothetical use cases that we see within the center. And then I'm going to talk about some of the surveys we've done to kind of understand usage within CHTC, talk briefly about things we're working on and things we're going to be working on in the future. So you may notice that I'm talking a lot about machine learning. Tony talked a lot about AI, and I think there may be some amount of truth from this comic here, but broadly speaking, artificial intelligence is the umbrella term. It's methods and software that enable machines to kind of see and react to different stimuli in an environment, enabling them to achieve a defined goal. Machine learning is a subset of that. It is specifically algorithms, practices to enable machines to look at data, learn from data, generalize pattern recognition that it has learned from the data in order to achieve tasks without additional instruction. So you often see this kind of Venn diagram in the artificial intelligence machine learning space. Artificial intelligence is the big outer circle. Machine learning is the inner circle, but then you have all kinds of ways to cover up the space more. So you have deep learning, which is a subset of machine learning. That's the application of artificial neural networks to kind of capture different connections between inputs and outputs. Under that, you have large language models, which are artificial neural networks designed to capture statistical connections and nuance of language. And then that one overlaps with something called generative AI, which is the models trained to produce data that looks a lot like input data. And then you have this intersection down at the bottom, and that's where your open AI, that's where your ChatGPT, that's where your Copilot lives, is this intersection deep, deep down. But like I said, this space is really complex. It's not even as simple, or this is an oversimplification. On top of that, you have things like data science. Where does that fit in this picture? Well, it intersects with everything. What about data engineering? Oh, it intersects with everything. Oh, what about academic disciplines like statistics and bioinformatics? Oh, those also intersect with everything. It gets really complicated really quickly. And we like to kind of keep it all at arm's length and say, we care about these things. There are, subtle differences and, implications for these exact differences, but largely, we think of these as black boxes that are tools and techniques and softwares that enable new and interesting and exciting science. So we try to keep it as much of a black box as we can, but there's complications. So we have to kind of dial back the opaqueness here and make it a little bit of a transparent black box. So what are some of these complications? Well, it's no surprise to anyone in this room. A lot of these things take pretty significant data and computing needs. A lot of benefit is gained by using GPUs, but those bring their own layers of complexities, right? So there's all kinds of hardware issues that we've seen in CHTC with communication dropouts. There's a whole slew of user education that has to happen in order to, make their software work. What is a capability? What does that mean? Users have to kind of learn how to use these resources effectively. There's also an administration cost, right? So TJ gave a great overview yesterday of some of the first-class features we've added to HD Condor in order to enable better utilization of GPUs within the pool. Then there's the cost and availability factor. GPUs are hard to get and they're very expensive. Another complication here is that this ecosystem moves incredibly fast. There's a lot of early adapter benefit to moving first and getting on top. So the net effect of this is that a lot of sort of simple copy and paste recipes tend to spread around faster. Users kind of find things that, oh, I want to apply this, I'll just copy and paste this recipe. But it's not truly educated. They're not really learning what's going on underneath. And the net effect is they come to us and say, well, I copied and pasted this recipe and it doesn't work as expected. What's going on? The other side of the ecosystem moving so fast and being so huge is that you get a lot of software stacks, you get a lot of layers of tools built on top of each other, which are all really similar, but they're not quite the same, and they all have slightly different interfaces. And so, a recipe that works for, say, Torch Elastic might not work for someone who really wants to use Hugging Face Accelerate. Very slight differences. They all accomplish the same things, but it's different enough to cause headaches. And then, the training process to train these models can take a really, really long time. And so we need to make sure that we are able to handle checkpointing as we go. And I don't think we've actually heard it. Oh, come on. I don't think we've actually heard it, but Marone often likes to say that there's nothing new under the sun, right? So it's something we hear year after year after year at this conference. These are not new challenges. These are things that, are things that we've tackled in the high throughput computing world, user education, scheduling, data movement, workflow orchestration. Nothing is new here. It's just kind of a slightly different, slightly new discipline, slightly new application. So in a lot of ways, high throughput computing and machine learning are kind of mirrors of each other. They're slightly different applications, but a lot of the same principles underneath. So that's what throughput machine learning is. That is the application of our tried and tested principles and technologies to machine. Oh, sorry, I lost my, oh, there it is, okay. To machine learning applications. And there are subtle differences that arise because of the nature of machine learning practices. So, data movement, we know how to do that, but the scale might be different. Our algorithm or our data drivers underneath, PyTorch, maybe that can start streaming data in. So maybe there are subtle differences in how we move and start to stream data in. Checkpointing, but we're doing this maybe at an epoch boundary in our training processes. We can use DAGMAN for a lot of these things, but there's a few extra bells and whistles that we can tack on. And I'll go through some of those later. And then again, GPUs are kind of a valuable and kind of precious resource. And so policy becomes very, very important. So again, I encourage you to look at TJ's talk from yesterday, but making sure we can schedule effectively, prioritize, preempt, all of those things become very important when we're talking about GPU utilization. So I'm going to talk through 3 different use cases in CHTC to sort of highlight a lot of these familiarities, but also explain through some of the twists and different applications that can apply. So let's say this handsome gentleman here comes and says, hey, I have 18 million scientific articles. This LLM thing seems pretty cool. I want to be able to search for, extract, kind of process and synthesize information across the entire corpus. He's pretty clever. He knows that this is a high throughput inference problem. So maybe his friend over in the Data Science Institute says, hey, I have a lot of experience with these LLM technologies and retrieval assisted generation. I'm going to help you build this pipeline. So again, this is a very, very familiar high throughput computing task, right? So this is maybe the twist here is just the utilization of GPUs, but this can be done for pretty much any kind of inference, any kind of prediction from an existing model. So what kinds of things fall into this category? A lot of large language models use embeddings. So this is kind of taking text and creating a vector representation in order to kind of measure sameness of different blocks of text. Again, predictions of any kind from any of Tony's fancy chemistry or biochem models, that falls into high throughput inference. And then something, we have a user who's doing large language model security studies. So trying to use different prompts to kind of escape the kind of security bounds within a trained large language model. So these are all inference problems that fit well within the high throughput computing philosophy. I'll skip over that for time. Another handsome person might come and say, I want to train many models. I want to discover which one of these are empirically, scientifically valid. I want to measure their predictive power, and I want to use these models to drive my science. So this is a high throughput training case. So this is kind of training a lot of, maybe small, medium, even big models to do kind of downstream science work, to do additional inference or kind of drive kind of secondary research. So examples of this might be just a hyperparameter optimization. That's what this top diagram here is. Just as we fiddle with these training parameters, what does the outcome actually do? How does it change? Another great example here is ensemble learning. I think of this as if you ask one fool a question, you'll get a foolish answer. But if you ask, a pool of fools, then you might get a better answer out of it. So getting more predictive power out of training a large number of models and using them together. Another example is fine tuning. It's very, very challenging to create these large language models. What's much easier is taking these pre-trained models and adapting them to your specific field by just doing some fine tuning. So that's what the diagram at the bottom here is. You essentially have this big giant box of weights on the left-hand side, and then you kind of create a secondary matrix. This is from the low-rank adaptation paper, which everyone should read because it's a really good one. But essentially doing lightweight, easier fine-tuning on top of big, heavy foundation models. And then again, we have a user who does ablation studies. So as we take features out of a model, how does the outputs change? And these are all throughput training tasks. And finally, we saw one on Tuesday, I want to say. So, he may be very ambitious and he says, I want to create one of these foundation models. I want to have this model that for all cell imaging science can be used to do inferences. This is something that's very big. It takes scaling across multiple nodes. And so this is something that I will call out Greg here as the so we put together this prototype workflow to kind of explore what kinds of things can we do that are kind of pushing the boundaries of the existing tools that we have, right? So there's a lot of challenges inherent in these big training processes, right? Within our pool, we have a lot of heterogeneous resources. We don't really want to mix generations of GPUs here. So we can solve this with requirements files. We have kind of an asynchronous, unpredictable schedule for when we actually acquire resources to be used. And this is something that actually PyTorch handles out of the box fairly well. A big thing here is that, as these different nodes are joining the training process, they need to be able to communicate with one central called the rendezvous server. And so this is something we put together, I think, a pretty clever DAG to handle, which I'm going to talk through because I think I actually have time. And then, another challenge here is performance. We're just kind of going to punt on that one for the time being. We're not going to be able to compare it to, the Metas of the world who buy 350,000 H100s for billions and billions of dollars. But this is, again, just an exercise in what can we accomplish using existing tools. What does this actually look? Okay. So multi-node training in CHTC is, again, this is kind of a prototype, a proof of concept. I wanted to include this because it does add a kind of some cool features to Hull's talk about DAGs yesterday, and then yeah, just kind of a few sort of neat features of Conduit that I wanted to call out. So the idea here is we need one worker to start training first. We need some rank 0 process to start. We do that by including a provisioner node. So provisioner node in a DAG is something that is guaranteed to start first. And once it starts, it communicates back. It says, OK, you can start the rest of the DAG now. I have started up. So what we do is we use that to kick off the process. And within that process, we run this, I don't want to call it a wrapper script, but essentially we kick things off and we have the machine use HT chirp to communicate back to the access point. I'm running on this machine at this port, have all of the other workers contact me there. And so once it's done that, once it's started up, then it can start the actual training process. And at that point, it kicks off the secondary nodes, which again, we have a prescript on that DAG node, which injects that actual server address and port into the process. And then the worker starts up and communicates back to the original rank 0 worker. So what does this look like? I don't know, I can whip through it here, but essentially it's, oh no, that was a little abacus. I had a little abacus to indicate that the computing was happening there. But again, the execute point, the first one starts up, communicates back to the access point and says, here's where the other workers need to go to communicate. And then that information propagates down into the secondary workers. Okay, so those were a whirlwind tour of 3 different kind of use cases, inference, throughput training, and then kind of a more ambitious multi-node training. I want to now talk about a brief survey we did. We looked at the highest GPU users of the pool, and we kind of asked, hey, what are you doing with these GPUs? Are you doing inference? Are you doing training? It seems to be a fairly even split between training and inference right now. We see a lot of PyTorch and PyTorch variants. That doesn't surprise me at all. But we also saw some mentions of Parabricks, which is an NVIDIA provided, I think, a sequencing tool. And we see a lot of different domains, a lot of bioinformatics, not surprisingly, a lot of people looking at LLMs, and we're also seeing some people doing interesting work with imperial machine learning, kind of trying to detect bias within models. I wanted to call out a few different pieces of feedback we got here. One user says, I'd rather see more small GPUs than get these big beefy H100s, which cost a lot of money. That's great. That fits beautifully into our high throughput computing philosophy. And we also, I like to fluff up our feathers here and strut our stuff a little. We had a user say that, oh, we're super thankful and you have enabled science that we could not possibly do without access to these GPUs. So that's always nice to hear. We like that feedback. We like bad feedback too. But okay, now we're talking a little bit about some of the ongoing work. So Christina gave a talk Tuesday about ongoing work with integrating Pelican and PyTorch for more effective delivery of data for training processes. This summer, we're working on a refresh of a lot of our tutorials and documentations around machine learning and GPU-based workflows. We're also working on some additional DAG workflows specifically for driving some evaluation and early abort of training processes. Once we've reached our estimation power that we want, then just stopping the training early. And then again, we want to keep talking to our users and understanding what exactly they're doing and what their needs are. I'm turning a little bit toward the future, sort of 6-month type plans. There's a lot of questions in this space. We want to be able to answer questions that are listed here, right? So if we're checkpointing jobs, if we start training a model on an A100 and then it gets evicted and then starts back up on an RTX 2060, what are the impacts of this kind of movement, this checkpointing process on the end predictive power of a model? What kinds of things can we do to more effectively move data sets for training and inference? Or we're addressing some of this with Pelican, but are there other things, other expectations that users have? Maybe they don't use PyTorch, and so we need to envision other ways of moving this data around. Then finally, what, if any, gaps exist for somebody who wants to do these large kind of ensemble models where they combine the predictive power of a lot of kind of smaller, medium-sized models? And again, this is a fast-moving field, so wherever AI development and wherever this community wants to take us is also something we'll be looking at in the future.